Hi, everybody. This is going to be our Sunday morning edition of reviewing for Chapter 10. Um, so ultimately, what I'm hoping that we're able to do with this is get ourselves to the point where I can go through again things that are the most important from your, I guess I would call it the final perspective. So after looking, we just kind of moved around a little bit for a few things. A lot of what you're going to be doing for the chapter 10 stuff is to talk about logs and how they're going to kind of work with each other, and then also do a little bit of work with laws of exponents, but it shouldn't be too bad. Let's talk about this for a second. Um, these problems here are asked to simplify or evaluate some of these things. And so let's for a minute just kind of remind ourselves what it means with a logarithm, how to go back and forth. So a logarithm is ultimately a way to isolate the exponent in an exponential expression. And so at its simplest way of thinking is that if you have something that's in exponential form, so if I have a base and I have raised that to an exponent and it is equal to some answer, then I can switch that into logarithmic mode by basically taking the base to tell us what our base would have been, moving the answer over here because we're saying, well, I want to know what exponent it is that tells me if the base is b and the answer that I get is a, what would the exponent for this be? So that's essentially what a logarithm is. It's just a way of going from an exponential form to a logarithmic form to isolate the exponent on its own. With expressions like the ones that you see here, what you tend to do is you are trying to take something like this and find out what that exponent would be. So if our base was 1/25th and our answer, or 1 over 25, and our answer was 125, what would the exponent be? And so the first thing that I would do in almost every single one of these situations when they're asking you to evaluate a log is I'd set it equal to an x. And then what I would do would be to put it in exponential form. So our base in this case is 1/25th. Our exponent that we're raising that to is the x power, and the answer that we would get to is 125. Now, we're going to get to more of these in a little bit, but what you're doing right now is solving an exponential equation. Um, most of these will be set up in such a way that if you're solving the exponential equation, you should be able to write both of your bases in terms of the same power. So in other words, if I look at this, 1/25th can have 5 as a power that would work for this, and 125 can also have 5. So if you can find a similar base to be able to write both sides of the equation as, you can solve it. So our first step is to put it in exponential form. And then what we have to remember is this. Here, 1 over 25 is the same as taking 5 and raising it to the negative second power. Because as we're looking at that, 5 squared is 25, and when it's on the bottom of a fraction, that's where we involve the negative exponents. This then is being raised to the x power, so that means that this is going to be 2 times that x, because you're raising it up to the top. Now, we also know that 125 is 5 raised to the third power. So once you've written the equation in a format where the base is the same, we can set the exponents equal to each other, and we can solve for x. So in this case, negative 2x is equal to 3, because if both of the bases are 5, the exponents have to be equal. And then if we take both sides and divide it by negative 2, we can get that x is equal to negative 3 over 2. So that is the simplification of what we're doing for a problem like that. In the next problem, when we're looking at the one that we have here, it's the same general idea. We set it equal to x. This one's messy because it involves a whole lot of stuff with roots and things, but it's the same process. Base is 4, exponent is x, and it's equal to the seventh root of 8 to the third power. That's a lot happening. So let's do this in a couple different ways. I think the first thing that I'm going to do before I try to get these as the same base is to rewrite this root and power dynamic as a fractional exponent. So what this actually becomes is 4 to the x is equal to 8 raised to the, well, when you do this, the index of your root is the denominator of your fraction, and the power that you have here is the numerator of the fraction. So this is 8 to the 3/7. It makes things a little easier to work with, particularly when we change both of these bases to 2. So here, 4 is just 2 squared. So that's 2 to the 2x. And 8 is 2 to the third power raised to the 3/7. Now, I'm going to need more space on this one than I gave myself because, again, wrote these reviews. It's long enough ago that it kind of is harder to look through. So when we look at this, this means that we're going to have 2 to the 2x is equal to, well, this is 2 to the third times 3/7. Well, the 3 and the 7 don't cancel, so this will become 9/7 when you multiply the 3 times 3/7. We still have 2 as our base. Well, now that the bases are set up in a way that they're equal to each other, we can set 2x equal to 9/7 and solve. Now, for me, I'm going to multiply both sides by 7 first because I hate having to deal with fractions all at the same time, and I don't want to divide it by 2. So we'll get 14x is equal to 9, and then I'm going to divide both sides by 14 and get that x is equal to 9/14. Again, a distinctly possible answer, but something that we want to be able to kind of think about as we go through and get to what we're doing. And this is the most difficult type of problem that you would see is something like we just did there. Okay, let's talk about ln for a second. It's a natural log. And one of the things that was important for us to think about when we have these is basically just what the base of this is. And here, the base of this problem is, this would be like log base e. Now, e, if we're looking for it, is just a natural number that occurs when you have some kind of compounding that occurs continuously. E functions as like pi. It's a representative of the number 2.71828. And it goes on forever irrationally. But this is log base e of the sixth root of e to the third power. We're doing this literally exactly the same way we did these last ones. We just have to remember that when I talk about an ln, it's just a base of e. So in this case, if I set that equal to x, well, that means that if I'm going from an ln to an exponential form, the base is e, the power is x, and it's equal to the sixth root of e to the third power. Nice thing about this is I don't got to do anything to the left-hand side. This is just going to be e to the x. Here, if I write this as an exponent, this will be 3 on the top and 6 on the bottom. So they've got the same basis. I'm going to reduce that fraction eventually, but it's essentially telling you that x is equal to that 3/6 because we have the same base, so we can just drop that base. 3/6 reduces to 1/2, and that's going to give us our answer for this problem. But it's just about remembering that when you're dealing with e as a base here, you're going to use the ln, or the natural log, to make something like that work. It's not hard, and essentially when they go through it, you're basically going back and forth between exponential and logarithmic forms. But that's what we're looking at. And another way that it could be written to you would be something like this. It's already in exponential form. And what you want to be able to do is to put it into logarithmic form. This one's actually not too hard to do. If I put this in logarithmic form, I'm going to write it with the base e, but you can also leap to ln as you do it. So if I write a log, the base is e, the answer that we're going to have is x, and that is going to be equal to 3 ln of 2, because that's what our exponent is up there. Now, here's what I love about this. Log base e, we know we can write as ln. So this is ln of x is equal to 3 ln of 2. Now, we're not going to be doing a lot with what's about to happen here. There's not a whole lot of laws of exponents that you're going to be using. And the likelihood is that you're not going to be dealing with a problem like this specifically on the final. But anytime that I've got a coefficient in front of a log, I'm trying to get it so that they're exactly the same, I can bring that up as an exponent. So this could be written as ln of x is equal to ln of 2 raised to the third power by taking that coefficient, bringing it up to the top. That's just one of our laws of exponents, or laws of logarithms. They have the same log. So just like what we did before with the dropping the base when they're the same, we can drop the log types when they are the same as well and say that x is equal to 2 to the third power, or 8, if you want to do the simplification of that. Just different ways of going back and forth. And anytime that you see an ln, if it helps you, just write it as log base e, and I think you can kind of work yourself through that. Okay, we're going to do a couple of these problems down here because we've done some with this already. But as you look at it, my suggestion is that we're trying to be able to combine everything on the left to be able to have it so that we have the same base on the right raised to a power. So these are solving exponential equations. It's the same idea here. And so when we do this, the biggest goal is that what you're going to be doing is combining everything on the left. So I always write everything in exponent form as opposed to radical form. It just makes it easier. So this will be a to the 5/4 times a Well, it's a square root, so that'll be the exponent 1/2 is equal to a to the x. This is a great problem because I've already just got the x there and I don't have to do anything with it. So I just have to combine those exponents. What we remember is that the law of exponents, where we're multiplying, it means that we add our exponents to put them together as one thing. Now, 5/4 plus 1/2, well, it needs to have a common denominator. So this is the same as 2/4. And so that would mean that when we combined them, this would be a to the 7/4 power, and that would equal a to the x. Got the same base, so I could tell you right now that x was equal to 7/4. Again, not a difficult problem, but one that you have to be able to apply some of your knowledge of how you combine some things to make that work. This one is a little bit more straightforward in that I don't have to do anything with the exponents right now, but I do need to write them with the same base. This is similar to some of the problems that we had done above, but we don't have to put it from log form to exponent form first. The bases that both of these would have in common is 3. This here is 3 to the 2nd power, and this here is 3 to the 3rd power. Now, for me, I'm going to write this one a little bit more precisely because we got a little bit of work to do. The power we're raising that to is 2x minus 3. Power we're raising this to is x plus 5. What's important about that is that we realize that when we combine the exponents here, we're multiplying them. So I'm going to have to distribute that 2 to both things to be able to get this as a combined exponent. So this will be 3 to the 4x minus 6, and this will be 3 to the 3x plus 15. What tends to happen in problems like this is that people always remember to do the first, but they forget to distribute to the second. So just make sure that you're doing both things as you do it. Now they have the same base as 3, so I will drop those bases and write just the exponents equal to each other. And then I'm going to get rid of the x from this side. Well, x minus 6 equals 15. I'm going to add 6 to both sides to get that x is equal to 21. And that gives us our answer. Now, we got a few more things that we're going to be doing with logs. Not a lot, but a few more. And so I'm going to bounce around a little bit for something like this. One of the things that you may be asked to do in situations like this is to solve problems. We're not going to do one like 16. This type of equation is not something we want to be able to jump to. But when you've been given problems like 14, 15, 16, or 17, most of what this is going to be is if you're solving for an unknown, your goal will be to put it in exponential form or in logarithmic form, whichever one you don't have, and then try to use that to figure out, like, what am I doing here to make this work? So here, because I've got log base 1/5 of x is equal to -1, if I'm solving for the x, the easiest thing to do first would be to write this in exponential form. Our base is 1/5, our power is -1, and that's equal to our x. So now all I have to do is evaluate 1/5 to the -1st power, and I'm good. 1/5 to the -1st power is just 5. So it's a pretty simple problem. It's just a matter of figuring out what it is that we would need to do. And the same idea here when it's written in log form. I'm going to have to take this and write it in exponential. So this is x to the 4th power is equal to 0.0016. Now, to solve this, I've got to get rid of that 4 now. It's a little bit different. So what I'm going to be doing is taking the 4th root of both sides. It's the same as raising it to the 1/4 power if you're using a calculator to do it. These two would cancel out. And if I'm being completely honest with you, when I recorded the secondary one, I don't actually have my calculator here with me. So what I'm going to try to do, and I don't know how well this is going to work, I'm going to see if it's possible to pull up, escape from the full screen. If I can, let's go that. I'm going to see if I can pull up Desmos to do this one so we can kind of look at it at the same time. So if I'm looking at Desmos, then what we'll do is I'm going to just, and this is the thing they gave you for your test. So I do, let's pull this guy up here. We will go 0.0016, that's 5. And I'm going to raise that to the open parentheses 1/4 power, because that's like taking the 4th root. And it's going to be 0.2. Again, that's not probably the best way for us to do it, but it's what we do when we're recording things. So x in this case, because those cancel out, is equal to 0.2. Boom. All right, back at it. So when I look at the rest of these then, again, it's the same idea here. These both involve e's. which is also fine. But what you want to be able to do is just to remember, if what you're trying to do is solve this, then you'll have to be able to write it in either exponential form or logarithmic form. For this one, ln is just log base e of 1 over x is equal to -4. And what I'm going to do is write it in exponential form. E to the -4th power is equal to 1 over x. Now, the fastest way to solve a problem like this one is to actually write the e to the -4th power. You could, guys, you've been able to solve for x in the denominator for a while, but for me, the easiest way to see it is e to the -4th is 1 over e to the 4th. If 1 over e to the 4th equals 1 over x, they both got 1 in the denominator, so I could tell you right now that x is equal to that e to the 4th power. And I don't need a decimal version of this. This is as simplified as I can get because since e is an irrational number, there's nothing else I can really do with it. By the same token, if what I'm looking at here is e to the 4x power is equal to 81, I could take this and write it in log form. So log base e of 81 is equal to 4x, or ln of 81 is equal to 4x. I'm solving that now for x. ln of 81 is something I can plug into the calculator. And I will, but I think the easiest thing that we can do before we do that is to solve for that x by putting it in what we call calculator ready form. And that means this is the thing that you could plug into your calculator, ln of 81 over 4. This tells me that you know how to go about doing this. And it tells me that that's the thing that you'd plug into your calculator. Now, the way that you plug this in, the decimals that you use, all that's fine. And I'm not worried about you being able to do that. So I'm not even going to plug it in right now because clearly I'd have to go to the Desmos and that takes a while. This is the sort of answer that we're looking for in a situation like that. So just make sure that when you're doing it, you're thinking a little bit about, well, okay, if I'm using log base e, remember that's ln, kind of work your way through. Okay. The last thing that we're going to be doing is a problem that involves compound interest, because we've done some problems with this. It's just been a little while. And so I want to make sure to kind of remind you how this works and what's going to happen. When we find a compound interest problem, this is a formula that's on your formula sheet. The formula is that the amount that you're going to have at the end is equal to your principal amount, what you start with, times 1 plus. Now, what you're going to be doing for this then is you're going to have the percentage rate in decimal form divided by the number of times that you've compounded this per year. So that's going to be your n. And you're going to raise that to the n times y power, where y is the number of years that this has occurred. So when we're doing this, the reason we're doing that is that ultimately what you're trying to do is you're doing what your percent is, and then you're raising it to how many times that you're compounding it. But if you compound it more than one time a year, you're dividing that percentage into that small amount, and you're compounding that many more times. That's why the n is used there for both. I can't remember if those are actually the variables that get used on your formula sheet, but it looks just like that. So if you're talking about how this would work, we're investing here $1,000, right? So that's going to be your principal, 1,000 times 10% APR. So I'm going to go the 1 plus, and we always do 1 plus because you're starting with 100% and adding the percentage that you're getting to that. So that's why you're adding this percent to it. So 10% APR, so that's 0.10 compounded quarterly. Now, quarterly is 4 times a year, so I'll put that on the bottom of my fraction. In this case, then, it's compounded for 6 years. So the 4, still the number of times I'm going to have to multiply it, but that is going to be times the 6 that I have here. So what I'm going to be doing is essentially plugging this bad boy into a calculator to get an answer for it. Now, I'm going to show you what that looks like, but we'll get to what it's going to be. Let me again move us to Desmos because, that's what we're doing. Okay, so when I get to this, let's make that go away for a minute. We're going to start with 1,000. So 1,000. Nope. Come on, Bechtel, get in there. 1,000 times 1 plus, and then I'm going to do a fraction. So it's going to be 0.10 divided by 4. And then I'm going to go to the outside of that, and I'm going to raise that. Now, I know that 4 times 6 is 24, so I'm just going to do that math. And so when we do that, we get 1808.725, blah, 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 blah. So that means that the answer for this is $1,808.73. Because if you look at something like this, you'll note that 5 that's next to it means the 2 goes up to the next nearest cent. So that's what we have here for the nearest cent. Now, The last part of it asks, how much time would it take to double your investment to the nearest year? These are really great problems to figure out because essentially what you're doing with these is you're going to be plugging them in to kind of a logarithmic sort of equation. So let me show you what we're doing. In the case of this, we wanted to double our investment. So I want this to become 1,000, become 2,000 when I look at the A that we have here. That's what the doubling would be. So if I'm setting the equation, 2,000 is my goal, start with 1,000, and it's equal to, again, all of this stuff on the inside is the same. So 1 plus 0.10 divided by 4. But if I want it to the nearest year, what I have to remember in this case is I don't know what that is. So we've got a little bit more work that we have to do here for a second. I am now solving an equation. Sometimes your unknown is going to be this one. Then you just have to plug all this stuff in and divide. Right now, my unknown's up in the exponent. So the first thing that I'm going to do is to take both sides of this equation and divide it by 1,000. So that what I'm going to get is that on this side of the equation, I'll have 2 is equal to this thing to the 4y. Now, for me, I'm going to go in and evaluate what this is so that I can have a much easier number to plug in. And I don't think it's going to be terrible. So let's try this for just a second. Actually, shouldn't be too bad. I'm going to get rid of this. And then I'm going to go over here, get rid of this 2. And then if I get rid of that exponent, okay, 1.025 is what my multiplier would then be. So that basically means that the 0.10 divided by 4 is 0.025. Not hard to think about. If you take 10 cents and divide it in 4, you're going to get 2.5 parts. So that is helpful for this. So that means that if I go back to the problem that I had here, what I'm going to have inside of this is 1.025. Now, I'm going to tell you what I would do at this point. Because we're raising that to the 4y power, and I want to solve this for y. What I would do first would be to actually raise this to the 4th power and just keep the y out here. It's going to give us a value. We only have one variable in the exponent. So I'm going to go back to Desmos, and I am going to raise this to the 4th power to see what we're going to have. That's crazy messy. I'm not going to do. Never mind. Let's go back to what we had before. I thought it would be nicer, and it's not. So let's just pretend like I didn't say anything at all. Okay, when I look at this, what I want to do when I have an exponential equation, the bases cannot be written the same way. I cannot write that as 2. What we then do is we take the log of both sides of the equation. Now, I'm not doing this half-life problem, so you're not going to have to deal with it, but I am going to keep solving this. So I'm going to take the log of both sides of this equation because what that will allow me to do now is this. I'm going to rewrite this problem below here. On the left-hand side, I will have the log of 2. Now, that's the button we have on the calculator. It's just the log button. I could put a base 10 because that's what the base of this common log is, but this is sort of what we're looking at. That is equal to the log of 1.025 raised to the 4y power. What we do in a situation like this that allows us to solve for that exponent is that we can then take that exponent and bring it all the way down to the front of our log. It's the law of logarithms that allows that exponent either to go to the front or back under simple. So now we have that the log of 2 is equal to 4y times the log of 1.025. Now, if I'm going to solve this, again, thinking of the calculator ready form, I want to know what that y is for the number of years. So I'm going to have to divide by that 4 because that's right here, and that'll cancel out. But I'm also going to have to divide by that log of 1.025 because I want this to cancel out too. What that allows me to do is then to set this thing and solve it for the y. Now that is what I'm going to plug into calculator. Telling you right now, it is not something you're going to be able to play with in a different way. But for me, if I'm going to divide it here, I would either use the fraction button or use parentheses around what you have here when you divide it. It is just a matter of what you plug in. What we're going to hope for is I can find a quick log button in here. So first thing I'm going to do is I'm going to type, well, let's see, logs anywhere. I'm going to look in the functions portion and hope for the best. I don't see them yet. Hey, look at that. It's a log. Okay. So we're going to do the log of 2. Close it. Divided by. It's a fraction on the bottom, which is lovely. So now we're going to do 4 times the log, I got to look for this too because it was in here. Log of 1.025. All right. Our answer to this is 7.01775. So what that means for our problem is that it works to about 7 years. It's a little more. 7.0 something means it's a little more than 7, but it does give us the idea, and the problem did tell us to round to the nearest year. Okay, you're not going to have to do anything else with logs for the rest of this. And most of the problems themselves probably won't take that long, but I think it's going to give you an idea as to what you need to do. And I think that's probably all you're going to need. So thank you.